Hi, I am Sanjay Patel. In this lecture, we are going to understand how to evaluate double integrals over a closed and bounded regions. In the last video, we have proved a result about how to compute double integral over a region using the concept of repeated or iterated integrals. So let us recall that result. So first of all, I will just show you what is the meaning of this double integral again over a closed region. Let us consider this closed and bounded region. Here our region is E and it is enclosed between this four curves. One is the line x is equal to A, the other is the line x is equal to B, and also between the two curves. So let us call this point as A and this point as B, where the two vertical lines are touching. Then the curve from A to B, let us take extra point over here, say ACB, this curve is given by y is equal to phi of x, and the curve A to D, ADB, say this curve is given by y is equal to psi of x. So our function is defined from this region to the set of real numbers. So our function f of two variables is defined like this over this closed and bounded region. So our region of integration is the area enclosed between the four curves, namely the line x is equal to A, x equal to B, the curve y equal to phi of x, and y is equal to psi of x. So whenever a region of integration is like this, then the double integral over this region is given by double integral over the closed and bounded region E of the given function is given by the repeated integral, say x is equal to A to B dx, and y is equal to say phi of x to psi of x f of x comma y dy. Okay, so whenever the region is enclosed between these four curves, the four curves you must understand they are this x is equal to A, x is equal to B, these two lines, and the curves y is equal to phi of x and y is equal to psi of x, where we assume that phi of x is always less than psi of x for every x between A and B. Okay, so if our function f of two variables is integrable, that is double integral exists over a region E, then this is given by this type of repeated integrals. Okay, and there is another option also. If the region is bounded between say the four curves in this way, say the four curves I am taking as y equal to C, the y equal to D, these two horizontal lines, and the two curves which are given by say this, if you take these two extra points to just specify more clearly, say point P and point Q, where the two lines are touching, then this curve is given by say x is equal to phi y, and this curve is given by say x is equal to psi y, is given by x is equal to psi y. Then in this case, okay, this part of this curve is given by x is equal to psi y. In this case, if the region is like this, then the double integral over the region E can be evaluated by the other formula which we have mentioned in that theorem also, and it is given by this thing, double integral over E of the function f dx dy is equal to integral say y is equal to c to d, y is equal to c to d dy, and integral x is equal to phi y to psi y of f of x comma y dx. So it is integrated with respect to x first and then with respect to y. Okay, here the four curves, you must note that the four curves are this: y equal to c, y equal to d. So these two lines which are horizontal, and the curve x is equal to phi y and x is equal to psi y. Okay, where phi is strictly less than psi for every point y between c and d. So for every y belongs to closed interval CD, we have phi of y is less than psi of y. So whenever a curve is enclosed between this, whenever region is enclosed between these four curves, you can compute the double integral by this type of, say, iterated integral. But remember, whenever a function f is integrable, both the iterated integral exist and they are equal. So we assume that all the known class of functions like continuous functions and some other kind of functions which are, say, nice, like continuous function, differentiable functions like that, these functions are always integrable. So every continuous function defined on this type of closed and bounded interval is always integrable, means its double integral always exists. So in all our problems, we always assume that the given function is integrable, just we learn how to compute the double integral using this technique. Just recall that these two integrals, one is this and the other is this, both are repeated integrals in the right hand side, and here this is integrated with respect to y first and then with respect to x, while this is integrated with respect to x first and then with respect to y. So let us solve some problems. So examples. The first one, evaluate the double integral x square y square dx dy over the region E, where capital E is the region, which is bounded by a triangle, whose sides are, you know, a triangle has three sides, so the three sides are, say, the line x is equal to 4, then line y is equal to x, and the x-axis, So this is our given region of integration E, which is enclosed between this three lines, yes. So first of all, we always draw the figure for this type of problem to get the idea how to write down the limits of integration. Okay, so let me draw the figure first. So let us take, say, x-axis, okay, then y-axis, let me take a y-axis, okay, make it small, fine. So this is x-axis, this is y-axis, and this is origin. Our region of integration is the area enclosed between the three lines. One is the line x-axis. You know the equation of the x-axis is y is equal to 0. So this is x-axis. First means one line. Let me make it with a different color because it is in use. So let me take this as green line. So this is one of the side of the triangle. Other side is say this line y equal to x, which I would like to draw like this. This is the line y is equal to x. Okay, and the third line I am taking here is, or the third side of the triangle is x is equal to 4. We always have to draw a rough figure. So suppose this is the line x is equal to 4. Okay, so let us name this. Say this is the line x-axis, which is given by the equation y equal to 0. Equation of y-axis, you know, x equal to 0. This is the line y equal to x, and this vertical line is x is equal to 4, and this point at which it is intersecting the x-axis is obviously 4 comma 0. This point is 0 comma 0. Okay, and our region of integration is this region, which is say bounded by these 3 lines. Okay, so this is our region of integration. You can immediately say what is the point of intersection of the line y equal to x and x equal to 4. By putting x equal to 4 in this, we'll get y is equal to 4. So this point is 4 comma 4. It is intersection of these two things. Fine. Now whenever a function is integrable, as I told you, all functions under consideration will be, say, integrable in our problems. So this function in x square y square, which is given here, f of x comma y is equal to x square y square is a given function. It is integrable over the region E. So its double integral exists over the region E. So we want to compute this double integral. But by the theorem, if the double integral exists, then it can be represented using the iterated or repeated integral. Here you can evaluate the double integral using any of the repeated integral because the function is integrable. So let us decide that you want to integrate with respect to, say, y first. Whenever you want to integrate with respect to y first, you always take a strip, say, parallel to y-axis in the region of integration. So let me take a strip parallel to y-axis in the region of integration like this. So which touches both the, say, ends of this region. Okay, you just move this strip throughout this region and check the lower end of the strip and the upper end of the strip must remain on the same curve throughout the region. Means even if you keep the strip over here, then also you can see the lower end of the strip is on this x-axis and the upper end is on this line y equal to x. So whether it is here or anywhere, for all position of this vertical strip, the lower end and upper end remains on the same curve. If it is not so, then we have to modify our region of integration, and those kind of examples we will take later on. This is the first one and the simplest one. So this strip means this is a vertical strip we are taking here because we want to integrate with respect to y first and find out the equation of the curve of both the ends of this strip. Okay, so we are integrating with respect to y first and then with respect to x. So this can be like this, say dx f dy, something like, say, x is equal to a to b and y is equal to phi of x to psi of x. So to compute this, we have to find this a, b, phi x and psi x. So what I am going to do is, I will find what is phi x, psi x and a and b. For finding phi x, psi x, a and b, you understand this these points. The lower end of the strip is given by the equation y equal to 0. This is the equation of the curve y equal to phi of x. And the upper end of the strip, which is lying here on this line, his equation is y is equal to x. So that is our psi of x. Okay. And to find the value of that a and b, okay, we always say start walking in this direction. Means from left to right, and see wherever we enter in this region from left to right. If you move in this direction, say suppose if you are walking in this direction, what is the first point that will occur? It is here. Okay, so this point is the first point, and for this point, what is the value of say x coordinate? The value of the x coordinate is 0. Okay, so that is your lower limit of integration of x. And when you exit the region, if you go on walking like this, when you leave the region, you are on this strip on this line x is equal to 4 on this vertical strip. So the value of x anywhere you take here, the value of x is equal to 4. Okay, so we have to find the values of the lower limit and upper limit like this. So it will be x is equal to 0 to 4 dx, and y is equal to phi of x to psi of x. So y is equal to 0 to y is equal to x square y square is the given function into dy. This means it is integrated with respect to y first and then with respect to x. Do you understand? So let me repeat. If you decide to integrate with respect to y first and then with respect to x, then you take a vertical strip, means a strip parallel to y-axis in the region of integration, and check all the positions of this vertical strip by moving it in the region of integration, and check that the lower end and the upper end of the strip throughout the region lies on the same curve. Okay, here throughout the region, the lower end is this x-axis given by y equal to 0, and the upper curve or the upper end is on the curve y equal to x. And to get the constant limits of integration of x, that is a and b, we always move in the region from left to right and see what is the minimum value of x and what is the maximum value of x. The minimum value of x in the region is 0 and the maximum value of x in the region is say 4. Or you can say whenever you enter in the region, what is the first point that occurs you have to consider and find the x coordinate of that point. So for example, if you move like this point is the first point and its x coordinate is 0, so we take x equal to 0 over here. And when you exit the region, when you come out of this region, you can exit from anywhere on this line. Either it is the same position. So the value of x on this line is x equal to 4. So there are two ways. We can check in this manner by entering and exiting the region to determine the limits of integration of x, that is constants, or you can find the minimum value of x when you enter the region and maximum value of x when you exit the region, and that is the limits a and b of x. And also the meaning of this double integral is this is equal to integral x is equal to 0 to 4 and integral y is equal to 0 to x square y square dy and dx. The meaning of this repeated integral is this. So many a times we don't write this step, we can write directly that this double integral is given by this iterated or repeated integral. This is iterated or repeated integral. Remember that. Now we integrate with respect to y first. So this is x equal to 0 to 4. And when you know that when you integrate with respect to y, the variable x is constant. So we keep this fixed, that I can put like this, and integration of y square is y cube upon 3. And then we have to substitute the limits of integration for this result for y equal to 0 to y equal to x. These are the limits of y, remember. And then whatever the result we get, that is to be again integrated with respect to with respect to x. So this is to be integrated with respect to x. Okay, fine. Now, substituting the limits of integration, we get integral 0 to 4, say, putting y equal to x first, we get x square into x cube by 3, and then y equal to 0, we get x square into 0 into dx. So the final answer is 0 to 4, of this integral, x is to 5 upon 5. Sorry, x is to 5 upon 3. The denominator is 3. And this is to be integrated with respect to x now. So it is a simple integral of our higher secondary course of one variable, which you can write immediately as x is to 6 upon 6, and 3 is there, and the limits of integration is 0 to 4. So this is equal to 4 raised to 6 upon 18 minus 0. Okay, so this is the value of this integral. So final answer is 4 raised to 6 upon 18. Remember, the function is integrable over this region, so it's both the repeated integral exist and are equal. So I can also compute the same problem, this double integral, using that second kind of repeated integral, as we'll see here in the second method or alternative method. Let me write that as an alternative method, say method 2. Okay, in this second method, we consider this same region again, and now our interest is to use the second repeated integral to compute the given double integral, which is this way: double integral x square y square dx dy over the region E. This I want to compute using the second repeated integral. In that case, what you have to do is you have to find the four curves. One is y is equal to c, y is equal to d, these two lines, and the two curves, so x is equal to psi y and x is equal to say phi y. As you know that, because the second repeated integral, it was given by say y equal to c to d dy, which is integrated with respect to x first. X is equal to say phi y to x is equal to psi y. So our interest is to find this limits of integration, and it is integrated with respect to x first. In such a case, that means whenever you want to integrate with respect to the variable x first, you always take a strip parallel to the x-axis in the region of integration. So I am taking an arbitrary strip parallel to the x-axis. So consider a strip like this, and always check that left hand curve and the right hand curve of this strip. Let me choose some other color. Say take an arbitrary strip parallel to x-axis, that is a horizontal strip, and for all the position of this strip, check the left hand curve and the right hand curve remains same. Means whether the strip is over here or here or here, the leftmost curve and the the left hand and the right hand point of this or end points of this strip are on the same curve. So here it is fine. So this is a nice or regular region, I will call it, and this left hand curve, which is same, gives us the equation of x is equal to phi y. You know, this is the line y is equal to x, which we can write as x is equal to y, and this as a function of say phi of y. Okay, and this finally, when you exit the region, this curve, which is the line given by x equal to 4, this is x equal to 4, that is my psi y. So equation of this point, this curve is x equal to 4, and equation of this curve is x equal to phi y. So to determine the curves phi y and psi y, we always take a strip parallel to x-axis or a horizontal strip and find out the equations of the curve as x in terms of y, means x as a function of y, from the endpoints of this strip. Okay, and to determine the constant limits of integration, that is this values of c and d, what we should do is we now move in this direction, say from bottom to top or in the upper direction, and see whenever we enter in the region what is the minimum value of y. When we enter in the region, we must enter through this x-axis. That is the first thing or the boundary of this region of integration which occurs in our way. So at this point, the minimum value of y is 0. You know, everywhere on this x-axis, the minimum value of y is say 0. And when you exit the region, when you move like this, and when you exit the region, what is the minimum value of y? You cannot take this point for the minimum value, because still the region is extended up to this point. The minimum value of y when you exit the region, this is not the end of the region. I can have the maximum value of y or maximum value of the variable y in the region is given by this point. So this is the last point when we exit the region. So the value of y is equal to 4. Or I can say, I can draw a line given by, say, y is equal to 4, like this. It is passing through this, and this line is passing through the point 4, 4, and its equation is y is equal to 4. So our curve is enclosed between y equal to 0 to y is equal to 4, that is c and d, and also between the curves x equal to phi y, that is x equal to y, this, and y equal to 0, that is again is x is equal to 0. X is equal to 0 is the equation of the curve. Okay, equation of the, our equation of the curve is x is equal to y, and this x equal to 4. This is the limits of integration of x. So finally, what I can write here from this figure is that this is equal to y equal to the minimum value of y is here, that is 0. Y is equal to 0 to y is equal to 4 dy, and the curves is first this curve, that is given by the x is equal to phi y, that is x equal to y, and when you exit the region, the curve is given by this orange line, that is x equal to 4, and the function is x square y square and dx. Okay, and this in practice we are writing directly in this form, that the double integral x square y square dx dy over the given region can be obtained by this second type of repeated or iterated integral, which is given by this x is equal to y to 4 x square y square, first with respect to x and then with respect to y. Okay, so this is equal to 0 to 4, y is equal to 0 to 4, and when you integrate with respect to, say, x first, this y is constant, so y square is constant, so I am writing y square as it is, and integration of x square is x cube upon 3, and this is to be evaluated from y to 4. Okay, and then we finally integrate with respect to y. Okay, so this is equal to integral 0 to 4 into putting the limits of integration. These are the limits of x, remember this is x equal to 4, so I will put wherever x is there. So first putting x equal to 4, we get y square into 4 cube upon 3 minus putting the lower limit of integration now, y square into y cube upon 3, and then it is to be integrated with respect to y. You understand? So y is fixed, y is constant, keeping as it is. These are the limits of x equal to y to x equal to 4. X equal to 4. So now we simplify this. X 0 to 4, y is equal to 0 to 4, and simplifying this, 4 cube upon 3, okay, 4 cube upon 3 into y square minus y raised to 5 upon 3 dy. So now integrating with respect to y, we get this 4 cube upon 3 is constant. Integral of y square is y cube upon 3 minus 1 upon 3 is constant, and integral of y raised to 5 is y raised to 6 upon 6, and then we substitute the limits of integration, that is y equal to 0 to 4. So putting y equal to 4 first, we will get 4 cube into 4 cube by 9 minus 1 by 3 into 4 raised to 6 upon 6 minus, putting the lower limit now, y equal to 0, so this becomes 0, and again here also it is 0. So finally what I will get is 4 raised to 6 upon 9, and here it is 4 raised to 6 upon 18. So 4 raised to 6 is common, and I can write 1 upon 9 minus 1 upon 18, and that is equal to 1 upon 18. Okay, so it is 4 raised to 6 upon 18, and this is the same answer as what we have obtained in the first type of repeated integral. It is also 4 raised to 6 upon 18. So by both the methods, whether you integrate with respect to x first or y first, we are getting the same value of double integral because the function is integrable, and we have noted in our earlier videos that if a function is integrable, then both the repeated integral exist and they are equal. Okay, we'll solve some more problems in the next lecture. This is just to give an idea how to compute double integral over a closed region. So have a good day. Thank you.